11:45, so let's go ahead and get started. And I'm recording this so people can look at it later if they want to. So who wants to get started with a question? Or do you want me to just briefly go over how to use the model set, or how do you guys want to do this?
Maybe let's start with a quick review.
Okay, so the basic concept of chapter 6 is what happens when you have a single carbon that has 4 different substituents attached to it, okay? So we have spent time before looking at stereochemistry, looking at what happens when you have a ring and things are pointing in different directions or in the same direction, right? You guys might remember that from chapter 2. There was a time when we talked about double bonds. Where are things located in a double bond can give you different isomers. So in this chapter, what we're doing is we're looking at a single carbon, like the one that I'm trying to hold here, that has 4 different substituents. And we're trying to figure out how does that affect the way that we can name that carbon and the way that we can do reactions with that carbon. I don't know if you guys got a chance to make any models yet, but the key to this chapter, the key to be successful in this exam is to have your model set with you, okay? You don't need the whole entire model set, you just need this much. You need a carbon for the middle, hopefully a white substituent, a blue, a red, and a yellow, okay? So that's what we're going to be needing for this chapter. You don't need the whole extended model set. If you left your model set at school and you don't have one at home, you can make yourself one, I don't know, out of marshmallows, olives, toothpicks, whatever you can find. All you need is to have these 5 pieces that I have here in my hand, okay? So as long as you have that much, you will be successful. It doesn't have to be the whole model set. Does everybody have a model set handy, or are you strategizing how you're going to make one? Everybody good? You know, you can give me a thumbs up. If you go to the bottom of the screen, you will see some reactions down there. And if you click on the one that looks like thumbs up, it'll look like this. Thank you. I see some thumbs up. Perfect. Oh, that's so exciting. So many thumbs up. If you guys don't have a model, this would be the time to improvise something, okay? And you're only going to need it for this exam so we can do the chapter 6 information. So we're gonna start there. Okay, so what is this chapter all about? This chapter is about molecules having mirror images that may be different from themselves. And the best example of that, you have it right in front of you, would be your hands, right? So if you can hold your hands in front of you, here I am. If you can hold your hands in front of you, wow, my hands look huge. You may notice that your hands are not superimposable. If you put one hand on top of the other, you see how the thumbs are pointing out in different directions? Parker, you're making me dizzy. And the reason for that is that your hands, if you put them right in front of each other, are what we call mirror images of each other. So if you look at your right hand and your left hand, the thumbs are pointing in opposite directions, and that makes them be mirror images of each other. So the word that we use for that in chemistry is, we call those things enantiomers, which is a word that I'm typing on the chat right now. Enantiomers are molecules that are mirror images of each other, okay? So if you have your model set handy, and we were in the classroom, I would ask you to make me a model of this molecule that I'm gonna type right here. I will ask you to make a model of bromo, fluoro, fluoromethane, okay? So I just typed it in the chat. And the convention here would be, please make your bromo blue, your chloro red, and your fluoro yellow, okay? That's where I would like you guys to start. So if you have your model set handy, I would like you to make a model of bromochlorofluoromethane. You're going to need 1 carbon for that because it's methane, right? And then I need you to put a blue, a red, and a yellow substituent, and you're also going to have a hydrogen at the back of it. Okay? I think Nicole made one. I see it there. And now, Nicole, you and I are going to figure out whether you and I have made the same compound or we have made 2 different compounds. How do you think we could go about finding that out?
I think the video showed them just like holding them over each other and seeing if all of the substituents ended up in the same position.
But you and I don't have a chance to hold them on top of each other because if I try to move into your square, Zoom doesn't work that way. So I'm going to propose that we do this. Hold yours by the white substituent, that is the hydrogen, okay? And make the other 3 substituents point to the camera. I see Ben is doing it as well. And I'm going to rotate this so that my blue substituent is on the very top, okay? My blue substituent is on the very top. Now, it looks to me like my compound and yours, Nicole, and the one that Ben is holding up all have the blue on the top, right? The red seems to be pointing to the left side of my camera and the yellow is pointing to the right side. Is that what you guys see as well?
Mm-hmm.
Okay, now don't change yours. I'm gonna make a small change to mine and I'm gonna put it back up, okay? So what I'm doing is I'm moving 2 of the atoms that I have on mine. And now, okay, there we go. Now, Nicole and Ben, do you think that you have the same compound that I have?
I think that I do and Ben does not.
Okay, so some of us are mirroring our camera and that's not helping us because we're seeing different things. But in any event, do you see different compounds on the screen right now? Some of them have the red in one place, some of them have the yellow in a different place, right?
Mm-hmm.
Yeah. Caroline, would you hold yours up too so you can participate as well? Who do you think that yours looks like? And again, you may be mirroring your camera, so don't worry too much. Just look for a compound that looks to you like yours. I can't hear you, Caroline. Sorry. Still can't hear Caroline. Anyways, the important thing here is that there are different forms of this compound, right? Whether we're mirroring our camera or not, we have different forms of this compound. Is that true?
Mm-hmm.
Okay. So what I'm going to do is I'm going to go into my video settings and I'm going to make sure that I am not mirroring my video. Okay, I am not. Good. If you guys want to go into your video settings, which is right next to where it says stop video, and make sure that you're not mirroring your screen, that would be really good because that way we all would be looking at the substituents on the same size. Okay, so the reason why this is important is because whether I have a compound that looks like mine or a compound that looks different or has the substituents in opposite locations, that is going to have a lot to do with the biological properties of that compound, okay? So the compounds that we're holding may all have the same kind of physical properties, but they don't have the same biological properties. Because to fit in the active side of a molecule, there's only gonna be one compound that fits in the active side. Does that make sense? So the importance of this having enantiomers versus not having enantiomers is that some specific enantiomers fit in some specific locations within molecules. Now, our job here is to figure out how can you tell that you can have enantiomers for a molecule? And the answer to that is you need to figure out if you have a carbon that has 4 different substituents, like we have here, okay? So I'm going to open our overheads for this chapter real quick so we can, so I can share my screen with you. And you can see some examples of those compounds that may have 4 different substituents on them. So let me go to chapter 6 and open the overheads. And we have covered the handedness part. Now we're going to talk about what does it mean to have 4 different substituents. Okay, so let me share the screen here with you guys so you can see the same thing that I see. There we go. So you should be able to see my PowerPoint now, and you should see the examples of enantiomers that are posted there. You guys see that?
Mm-hmm.
Okay, so the compound that you guys just made, the compound that I asked you to make, is similar to the one that is down here, okay? It has a hydrogen substituent, and then it has 3 substituents that are different from each other. Those carbons that have 4 completely different substituents are what we call stereocenters or chirality centers or chiral carbons, like you heard on the video that you guys saw for this chapter, okay? Chiral carbons are the ones that allow you to have 2 different mirror image forms of a compound. So a compound like this will have 2 enantiomers, okay? This is one enantiomer, this is the other enantiomer. Can you guys see that? Okay, now look at a compound like the one that we have here on the top. Okay, this compound that we have here on the top has 3 identical hydrogens on it. When you have 3 identical substituents on a carbon, like 3 identical hydrogens, can you see that these 2 compounds, even though they're mirror images, if I took this one and I lifted it up and put it on top of this one, can you see how they would be superimposable? If I took this compound and I magically moved it and put it on top of this one, would the hydrogens line up on the bottom? They would,
Yeah.
right? Because these 2 compounds are the exact same thing. So there's 2 options that you can have. You can have compounds that are the same thing, in which case you don't have any chiral carbons in that substance, or you can have compounds that have 2 mirror images, like the ones that you are holding in your hand should have a mirror image that we can look at. How do we find that mirror image? Well, you can make 2 models and you could put them right next to each other to see if they're superimposable or not. That would be one option. And the other option would be to make sure that you have 4 different substituents on one carbon. If you have 4 different substituents, you can consider that that compound has a mirror image, which means it has 2 different enantiomers, okay? So let me put together 2 mirror images so I can show them to you. And in the meantime, we can talk about any questions that you might have so far. Oh, I'm missing a yellow substituent. Okay, back to the drawing board. Let me make this with a different model set. Any questions so far, guys? Did anybody attempt to work on the problems that are posted on Moodle and have any difficulties with these problems?
I was having a problem with the last, I think it was.
Ben, can you talk a
4.
little louder? I can barely hear you.
Yeah. Is that better?
Yes, much better. Thank you.
I was having a problem with the last, I think it was the last problem 4, because it's attached to 4 different molecules, but 2 of them are carbons that are then attached to different things. And I was having a hard time like figuring out what the chiral site was supposed to be because of that.
So when you have carbons on both sides of a chiral center, you keep looking until you find the point of difference. If you cannot find the point of difference, you don't have chirality, okay?
Okay.
We will, I will put some of those on the screen and we can work on some examples. But that's a very good question. When do we stop when looking for chiral centers? We don't stop until we find a point of difference. That's the most important thing that we can do here, okay?
Okay.
Okay, so let me show you the 2 molecules that I have here. and see if we can solve our mirroring problem. Okay, so here's one of the compounds that I made. Let me put myself back on full screen so you guys can see me better. Okay. So here is one of the compounds that I made, and here is the other one. Okay. I know that these compounds are mirror images of each other because if I put them right in front of each other, they can, let's see. I wish I could get my hands out of the way. There we go. Can you see how everything lines up if I put one in front of the other? Is that obvious to you guys? See, the reds are in the same place, the blues are in the same place, and the yellows are in the same place? Yeah? Okay, so they're mirror images of each other. Now, if I take one of them and I try to superimpose the other one on top, let me get back a little bit so we can fit all that in the screen. If I line up my hydrogens, which is what I'm doing right now here on the top, look what happens to the other substituents. I can line up the reds, but on this side, I have a yellow and a blue. And on the other side, I also have a yellow and a blue. That's what we call two molecules that are not superimposable, okay? I can't put one directly on top of the other one. One of these molecules is what we call an R enantiomer, and the other one is what we call an S enantiomer, okay? Nicole, you want to show us the ones that you're holding and see if they're mirror images of each other?
So they are mirror images.
Hold them by the hydrogen and see if they can see each other in the mirror.
They can, but they're not enantiomers.
They are enantiomers because they're not superimposable. They are enantiomers of each other.
But they're not what?
They're not the same thing.
Okay.
They're different compounds.
Okay.
So now we're going to work a little bit on figuring out what the how to determine if the enantiomer that you're holding in your hand is the R enantiomer or the S enantiomer, and then we're going to work on some problems. Okay. So hold whichever one you want, whichever one you just found in your hand. And this is what we're going to do. This is what the rules say, okay? We're going to rank those substituents in order of priority according to the easy system. The rules are the same as we use for the easy system. And the convention that I like to use is I like to put my highest ranked substituent, I want it to be blue. The second highest rank, I want it to be red. And the third highest rank, I want it to be yellow, okay? That's the reason why on the chat, I ask you to make the bromine blue, the chlorine red, and the fluorine yellow. Because who has the highest molecular weight between those three things? Is it bromine, chlorine, or fluorine?
Bromine.
Right? So this is bromine, has the highest ranking, and that's why we're making it blue. This is chlorine, second highest ranking, we're making it red, and this is fluorine, lowest ranking, we're making it yellow. Everybody has a model that they can look at? Okay, now the rules say that you're gonna hold the model with the hydrogen pointing away from you. Okay, so hold the model so that the hydrogen is pointing away from you, and that should give you a triangle right in front of your face, and it's gonna look like that, and it's gonna have the three substituents that are facing you. Is everybody able to do that? Yeah? Okay. Now, with your hand, you're gonna trace a big circle in the air that goes from blue to red to yellow, okay? Make the circle as big as you can. Tiny little circles don't help. You're gonna go from blue to red to yellow. And in my case, if I were to do that and I went from blue to red to yellow, I'm going to the right on my molecule that I have in my hand. You guys may be going in a different direction because you have different compounds that I have, okay? Some of you were tracing a path that took you to the right. Some of you were tracing a path that took you to the left. Those of you that were tracing a path that goes right, like this, are the ones that are holding R enantiomers in your hand. So if you have an R enantiomer in your hand, can you lift it up and put it on the screen so we can all see that you have an R enantiomer? Okay, I see a lot of R enantiomers. And now some of you, when you trace a path from blue to red to yellow, you are going to the left. So you have what is called the S enantiomer. If you have the S enantiomer, can you put it on the screen so we can see it? I see Nicole has one and Ben has one. Those are all the ones that I can see so far. And I think James has one as well, right? So you guys were going, when you did your big hand gesture, you were going to the left. Is that correct, guys?
Mm-hmm.
Yeah, okay. Now, one thing that we know from our research is the bigger the hand gesture, the more accurate you're going to be, okay? Tiny little circles with your finger, not very helpful. Big hand gestures with your hands, really helpful in finding the correct answer. So you're going to be taking this exam at home, hopefully all alone. So I want you guys to do your gestures as big as possible, okay? Because that will increase your accuracy when answering these kinds of questions. Do you feel even remotely comfortable with finding R and S enantiomers so far? More or less comfortable? Okay. So Tim, I know you still have some questions about that problem number 3, and Christine, I see your questions too. I'm going to show you a few things about chiral centers with our overheads, and then I'll put the homework on the screen and we can work on those, okay? So bear with me, we're gonna get to it. Okay, so chiral centers or stereocenters or chirality centers, all those words describe the same thing. And what they describe is a carbon that has 4 different substituents attached to them. So Ben, you had just asked me, when you have a carbon that has carbon substituents on both sides, how do we know if they're chiral, right? So here's an example that might help with that. Look at this carbon in the middle, the one that has the star, the black one, okay? It has a hydrogen substituent, it has a bromine substituent. It's very easy to see that the hydrogen and the bromine are unique substituents, right? That's not a problem for anybody. Now we have a CH2 on this side and a CH2 on the other side. Should we consider that these 2 things are identical and stop now, or should we keep looking?
Keep looking.
Thank you, Nicole. Everybody, Nicole is the only one that's talking to me and feeling a little lonely here. Okay, so we're gonna keep looking. The next thing that you get after the first CH2 is another CH2 on this side and another CH2 on this side. Should we keep looking?
Yeah.
Yeah, keep looking. So if we keep looking for the 3rd time, we're gonna find another CH2. By now we're getting a little desperate, right? How much longer are we going to keep looking? Look, when we get to the 4th carbon, what happens? On this side, the 4th carbon is a methyl group, but on this side, 1, 2, 3, 4, the 4th carbon is a CH2. Did we find the point of difference? Yes, we did. Therefore, this carbon right here in the center is what we call a chiral carbon. Does that make sense?
Mm-hmm.
Yeah.
Ben, did that answer your question about how far we had to go to find the difference?
Yes.
Very far, okay? If you don't have the same patients and you don't want to go one group at a time, what you could do is what we did here on the side, where you name the substituents. If the names of the substituents are different, that will tell you that you have found a point of difference, okay? If these 2 substituents were identical, they would have the same name, and they don't, okay? So that's a shortcut if you're too impatient to go carbon by carbon, which I don't know that anybody of us can afford to be too impatient because we have to take a test, but just in case, it can also serve as a verification tool, okay? Name the substituents and figure out what's going on.
So if you were to go back to that, how
Yes,
would you
ma'am.
determine which one has a higher ranking?
Between the butyl group and the pentyl group,
Yeah.
pentyl group would have a higher ranking because if you go carbon by carbon, this is identical, this is identical, this is identical. This one ends on a carbon, but this carbon is attached to another carbon. So the
Okay.
bigger substituent is going to have the bigger ranking.
Gotcha. Thank you.
No problem. Good question, Carrie. Okay, now chiral centers in rings, those usually give people a very hard time. We're gonna apply the same logic. We're going to look for a point of difference. If we find a point of difference, then we have chirality. If we don't find a point of difference, we won't have chirality. For example, let's consider carbon 1 on this ring that we have here, okay? Carbon 1 has a hydrogen attached to it, and it has a methyl group attached to it. Those are two unique substituents, and I'm pretty sure you guys are pretty comfortable with those two, right? But then we're gonna look at this ring. Coming out of this carbon, if I go this way, I'll find the CH2. If I go this way, I will also find the CH2. Have I found the point of difference? CH2,
No.
CH2, are they different? They're the same,
Yeah.
right? Let's go down here to carbons 3 and 5. Are they the same? Are they identical, 3 and 5?
Yes.
Yeah, they're the
Yeah.
same.
How about carbon 4? Carbon 4 was my last hope for a difference. Is carbon 4 different from
No.
ones that we have seen before?
No.
No.
So the view on this side of the ring is identical to the view on this side of the ring. And that means that there's no chirality on this carbon. That carbon is not a chiral center, okay? Now let's try this example here, the one that has the star, okay? Carbon number 2. Look at it this way. If we look at this side of the ring, carbon number 1, we find the carbon that is double bonded to oxygen. If we look on the other side, we find the CH2. Are those two things identical?
No.
No. So what is your expectation for the carbon that has a star here? Will it be a chiral center or a chiral carbon? Yes.
So, yes.
And the reason for that is that you have different substituents on each side of that ring. Okay? So I'm going to stop sharing the screen for a second so I can check what's going on in the chat. There's nothing new on the chat. If you don't have a microphone, you can send me your questions via the chat. If you do have a microphone, use it so we can continue looking at the overheads. So we're going to skip all the adventures of Louis Pasteur, which were very interesting, but we're going to skip those in the interest of time. The sequence rules are the same rules that you use for the EC system, okay? Highest molecular weight at the first point of difference, that's what we need to be looking for. So let's look at, I know that I have a big, okay, perfect. This is a place where we can practice our enantiomers before we take a look at the problem that's posed to on Moodle. So in nature, there are many compounds that are chiral. And here's an example. Limonene is a compound that you guys are very familiar with as the smell of citrus fruits. But I bet you didn't know that limonene has another enantiomer that is actually the smell of pine trees. Does this give you an idea of how different two enantiomers can be from each other? Would you ever confuse the smell of an orange with the smell of a Christmas tree?
No.
No, right? Your nose can smell an orange and tell you immediately with your eyes closed, this is an orange. And you can smell a pine tree and you will know this is a pine tree. The smells are completely different. The compounds are binding different receptors in your nose, which is sending a different signal to your brain. So I don't think that you would casually confuse lemons and Christmas trees. The two compounds, as you can see here, are nearly identical, and they only have a very tiny difference, which happens on this carbon right here, okay? So let's figure out why this carbon is chiral. There's a hydrogen substituent here, okay? There's this substituent that is pointing towards the back. That's what that is. And it has 3 and a double bond. You see that guy back there? Oh, Nicole, who is this precious little dog that just walked in?
This is Riz.
What's his name?
Riz.
Hi. Oh my goodness, what a cutie pie. See, we can't do this in class, so it's fun. It's fun to see everybody's dogs. Okay, pay attention, buddy, because we're learning about enantiomers here. We're learning about chiral carbons. So still looking at this carbon over here. There's a hydrogen on the top. There's this big compound that is pointing towards the back here. Now let's concentrate on the ring, okay? If you look at this side of the ring, you will find CH2, CH2, and then this methyl substituent way further back. If you look at the bottom of this ring, you will find CH2, and you immediately come to a double bond. Is the top part of this ring different from the bottom part of this ring? They are different, right? Can everybody see that they are different? So that means that this carbon that we have here is indeed a chiral carbon, okay? The same will happen on this side. You have a hydrogen, you have the substituent that is pointing towards the back, and you have the two sides of the ring, and the two sides of the ring are different, and that means that this carbon here is a chiral carbon, okay? Now, I know you're looking at this plus sign and this minus sign here. I'm wondering what that's all about. Those plus and minus signs are some very, very old nomenclature that people used to use before we knew that there was such a thing as R and S enantiomers, okay? So limonene, if you buy it, you can still buy plus limonene or minus limonene. The plus smells like citrus, the minus smells like pine trees. It's a really old nomenclature, but that's not the one that we're going to use. We're going to use R and S, okay? Excuse me. Okay, so there's a problem here on the slides. Can everybody see that? Can you see my screen? So this compound is actually a natural precursor of erythromycin, which is an antibiotic. And we're gonna look for chiral centers in this compound. So I hope you have your pencil sharpened because there's a lot of chiral centers here, okay? Does anybody want to tell me what kind of things we could rule out right now because we know they cannot be a stereocenter? Anybody be a candidate to not be considered here? Let me give you an example. This carbon here in this methyl group, could that carbon be a stereocenter?
No.
No,
What does the dog say? We want to know the dog's opinion, Nicole.
he agrees. It's a no.
He agrees, okay. And why does he agree? Because that carbon has what?
It doesn't. It has 3 of the same substituents.
It has 3 of the same substituents, so that guy cannot be a chiral center, okay? So that's gonna allow us to rule a lot of possible candidates very fast, because if you have identical substituents, you cannot be a stereocenter. So this methyl group cannot be a stereocenter. How about this methyl group? Can it be a stereocenter? No. How about this one here? No. None of the methyl groups that are attached to the outside of this compound can be a stereocenter because they have identical substituents, okay? So we can rule those out. The other carbons that can be ruled out very quickly are any carbons that have double bonds on them. So for example, this carbon here that has the double bond to oxygen, we would consider that double bond to oxygen as a repeated substituent, okay? That carbon is bound to the same thing twice. So any carbon that's in a double bond cannot be a chiral carbon. So you can see how this guy is not a candidate, right? There's another one down here, another carbon that is double bonded to oxygen. That cannot be a chiral carbon as well. I'm pointing to this carbon right here. Y'all can see my cursor, right?
Mm-hmm.
Okay,
Yeah.
so that carbon cannot be a chiral center. There's still plenty of candidates left. So I don't know where you guys would like to start. I think I'm gonna start right here. I'm pointing to that carbon right there on the side of the oxygen that has the double bond. Do you guys think that that carbon could be a chiral carbon?
Yes.
What substituents does that guy have? It looks like it has a methyl group, right?
Mm-hmm.
It has this side of the huge ring, which goes to a double bond to oxygen, right? This side, which goes to a CH2, and that's a line structure, so there's a substituent that's not being shown. What is the substituent that's not being shown in the line structure?
A hydrogen.
Hydrogen.
A hydrogen, right? So does that carbon have 4 different substituents?
Yes.
Yes, it does. So that is what we call a chiral carbon. Okay, this carbon right here is chiral, is what we call a stereocenter. So show of hands, does everybody understand that what we just did right now, that that particular carbon was a stereocenter? Yes or no? Thumbs
Yes.
Everybody thumbs up? Okay, guys, if anybody did not get it, this is the perfect time to ask a question because we are not telling anybody. So,
I have a question.
yes.
For like the carbons that it's attached to with the double bond, would that just be, you said it is H and the other one would be a CH2?
Yes. So let me put that back on the screen. Just to make sure that I understand your question correctly. You are asking me if I'm looking at this carbon right here, right?
Mhm.
On the one side, I have this carbon that goes to the double bond on oxygen, and on the other side, I have the CH2. Is that what you're asking me?
Yes.
Yes. And can you see how those two are two different substituents?
Mm-hmm.
Because being a CH2 is not the same as being a carbon double bonded to oxygen, right? And then the fourth substituent, the one that's not being shown here, is a hydrogen because we are in a line structure. Does that make sense?
Yeah.
Okay, so I'm gonna point to the next carbon here. I'm looking at this carbon. I hope you can see my cursor. This carbon right here on that side of the ring. That's such a huge ring. It's hard to get your bearings, but looking at that one. Does anybody want to help me figure out if that carbon is chiral or not? Any suggestions? What kind of substituents do you see on that carbon?
We have, we know that there's 2 hydrogen substituents.
We know that if we're in a line structure and we can only see 2 substituents, the other 2 substituents that are not shown must be hydrogen, right? If it has 2 identical hydrogens, can that carbon be chiral?
No.
No. So this guy is a no. That one cannot be chiral. Everybody got that? Okay, let's move to this guy over here. This one is not even hiding anything. All the substituents are visible. So tell me what you think about that one. What kind of substituents do you see on that carbon?
An alcohol,
There's an alcohol directly attached to it. That's true.
a methyl,
A methyl group.
and then
On the bottom, you go to this CH that has an OH attached to it, right?
yep.
And on the top, you go to the CH2. Is this guy different from this guy? This
Yeah.
H2 different from this CHOH?
Yes.
Yes. So this carbon must be a chiral center. Are you guys getting the hang of how to find them? More or less? You want to see how many total chiral centers are in this compound? Everybody that has a star is a chiral center, okay? You see that? That is a heck of a lot of chiral centers. And that is the only form of that compound that is biologically active. If you get a single one of these chiral centers wrong, you will not be able to make erythromycin and it will not be an antibiotic. It actually might be toxic, so you have to be very careful with it. Look at those compounds that have, look at those carbons that have the little stars there. Does any of those surprise you? Does any of those look to you suspicious or like it might not be a chiral center? I have one that students always ask about, but I want to hear what you guys have to say.
So I question the carbon that's attached to the double bonded oxygen and the oxygen. I mean, I can see
This
how they're
one
both.
here?
No, the lower one.
This one?
Yeah.
Are you questioning this carbon next to it?
No, because I can see that one has a different sub, but that
This
carbon.
one?
Yes.
Okay. Do you see, is this Christine?
Yes.
Okay, Christine, do you see that that carbon is bonded to oxygen twice? Because it's double bonded to oxygen?
Okay, you said double bonded ones don't count.
Not be chiral themselves.
Okay.
This carbon here and this carbon up here cannot be chiral because they're bound to oxygen twice. So they themselves cannot be considered chiral.
Okay, thank you.
The same is going to be true whenever you find a carbon that's double bonded to another carbon or a carbon that's triple bonded to nitrogen. If a carbon is in a multiple bond, that carbon itself cannot be chiral.
Okay, that makes sense. Thank you.
Okay, let me show you a carbon that a lot of students ask me questions about. This carbon right here. You see the star that I'm pointing to? A lot of students struggle to see how that carbon is chiral, okay? And I think this is the reason why they struggle. Everybody knows what carbon we're talking about now? Because I'm gonna move the cursor. This carbon. Okay, so look at the things attached to this carbon. It's a line structure, so there's a hydrogen that's not being shown, right? So we have a hydrogen. We have a methyl group. If you look this way, you will find a CH2, a CH with an OH attached to it, right? If you look down here, you will also find a CH with an OH attached to it. So far, it looks like this side and this side are looking the same. Do you all see that as well?
Yeah.
So what do? Do we stop there or do we keep looking?
Keep looking.
We keep looking, right? So if you keep going up here this way, you will get to this carbon that has OH and CH3. And if you keep going down here, you will find a different landscape, right? You will find only a CH3. Have we found a point of difference when we look further in each direction?
Yeah.
Yes. So is this little guy here a chiral carbon? Yes, it is. It was a little challenging because we had to search a little bit further, okay? And sometimes you're gonna have to search really far to find the chiral carbons. Does anybody have any other question about this particular picture that I have up here, or can I move on to the homework?
I'm good.
We good? Okay, so let me move on and check the chat. Okay, everybody seems to be doing okay and going along. So let's move on to the homework screen. So don't freak out when you look at my Moodle. My Moodle looks a lot worse than yours because it has a lot of stuff going on. Just ignore all of that. There is the homework assignment that we're going on. And we're going to look at the questions that are on that homework assignment, okay? And sorry, I don't want to show you any names. So I'm going to stop sharing the screen for just a second, just so I can open a question. Sorry guys, trying to respect FERPA rules and do the teaching online at the same time. And I saw that some of you have questions about number 2. So we're going to start with that one. Okay, and I think if I move this here, you won't see any names. Perfect. Okay, so give me just a second. So let's share that screen with you. And it should look like this. Okay. Can you guys see that I have question 2 on the screen? It says which pair of structures are enantiomers?
Yes.
Okay. So the way to solve these kinds of problems is always to make a model and use your model to figure out whether you have an R or an S enantiomer in front of you. Okay. That's the most important thing. So let's try our luck with the first compound that we have here. We're going to make a model real quick and we're going to determine whether it's R or S, okay? So for the rankings that we're going to use, our highest rank substituent is going to be blue, our second highest rank is going to be red, and our third highest rank is going to be yellow. Does that order make sense to you guys? Blue, red, yellow? I mean, it is not completely arbitrary. If you ever went and did anything, any kind of 4-H, FFA, any kind of animal show of any kind, the blue ribbon is the first prize, the red ribbon is the second, and the yellow ribbon is the third. That's where that ranking comes from. Also, blue, red, and yellow are in alphabetical order, okay? So whatever works for you, blue, red, yellow are in alphabetical order. Some people never get completely comfortable with the blue, red, and yellow dots. So you might want to have to write with a Sharpie the numbers 1, 2, and 3 onto your model set so that you know what the ranking is, okay? We need to make sure that we get comfortable with the model set before we get to the exam. Okay, so let me ask you guys, if we're going to be ranking the substituents, we know hydrogen is gonna have the lowest ranking, right? Because hydrogen is the smallest of all the substituents there. Here we have a carbon in this methyl group. Here we have an OH, and here we have a carbon double bonded to oxygen. Of those three things, who has the highest molecular weight? Carbon, oxygen, or carbon?
Oxygen.
Oxygen.
Oxygen has the highest molecular weight, so is it clear to you that this ought to be your blue substituent? Yes? Okay. And then straight up here, you have a carbon that has 3 hydrogens attached to it. And down here, you have a carbon that's double bonded to oxygen and then single bonded to oxygen. Between the substituent on the top and the substituent on the bottom, which one do you think should have the second highest ranking? Which one should be a red substituent?
The bottom.
The bottom should be a red substituent because it has the higher molecular weight things attached to it, right? And then the methyl group is going to be our lowest ranked, and it's going to be our yellow, and then the hydrogen is just going to be the super low rank. So let's build a model that reflects what you can see here on the screen. Okay, you could hold your model set with the hydrogen pointing towards the back, with the hydrogen pointing as far away from you as possible. Can you guys see me on camera besides the shared screen? Can you see
Yeah.
the model set?
Mm-hmm.
Okay, thank you, Caitlin. And now let's put the other substituents in there. What should be pointing straight up? What color should be pointing straight up?
Yellow.
Yellow should be pointing straight up. And if let me put this away from you. The hydrogen is facing away from you. The yellow is pointing straight up. Who should be down and on the plane next to the yellow? What color was the OH group?
Blue.
The OH group was supposed to be blue, right? And it's supposed to be on the plane and next to your yellow substituent. And then your red substituent, which is the last one, should be pointing towards you on the bottom. Did everybody build a model of that? So here's the model that I built, and I'm gonna hold it facing away from you. And I'm going to ask you, if you're going from blue to red to yellow, which direction are you going? Are you going to the right or are you going to the left?
Right.
Red to yellow. Which direction are you going?
Left.
Blue, red, yellow. Are you going to the left?
You're going to the right.
So let me ask you one more time. Let's make sure that your model set really reflects what you can see here on the screen. Your yellow substituent should be pointing towards the top. Your blue substituent should be next to the yellow on the plane right here. Your hydrogen should be going away from you on the back, and your red should be coming towards you here on the front. This is blue, this is red, this is yellow, okay? Does your model reflect what you see on the screen?
Yes.
Now, if you're going from blue to red to yellow, which direction are you going? Are you going to the right or are you going to the left?
Left.
To the right.
I'm
You're going
to the right.
clockwise.
I'm going to the right on mine, which would be the equivalent of going clockwise. Is that what's happening to everybody?
Yes.
Caitlin, is that what's happening to yours?
Yeah, it's like wax on, wax off.
Yeah, wax on, wax off. That's right. That's a very good analogy. So right now we would be putting the wax on, right? We're going to the right. So this is the R enantiomer of this compound that we have here. Did everybody find the R enantiomer? Yes. For the next one that is over here, as you can see, they have moved the whole molecule around, but not only did they move the molecule around, they moved the substituents too. So let's build a model. Make your hydrogen point straight up right now. And on the plane in front of you, you should have a red substituent and you should have a hydrogen. So before you add the blue and the yellow, you should have something that looks like this. Y'all have that? This is the hydrogen that is pointing towards the top. This is the carboxylic acid that is pointing to the side. Does everybody have one of those? Now add your yellow, which should be pointing towards you, and your blue, which should be going away from you, okay? I can wait for you to get it done. And now we're going to make a path with our hand from blue to red to yellow. Which direction are you guys going? Is that right or left?
Wax
Left.
off.
Everybody's driving the bus. Are you turning right or are you turning left?
Left.
Left, right? So can you see how this is supposed to be the S enantiomer of that compound?
Yes.
Okay, so you got it. This is R and this is S, right? So are these two things enantiomers of each other? Yes,
Yes.
they are. They are enantiomers of each other. Now we have to do the same thing with compound number 2 and with compound number 3. Now, I can see how compound number 2 might be a little bit scary because it doesn't look the same way as the things that we had here, right? It doesn't have those two solid lines that really make it easy for you to orient yourself. This compound, when you build that model, there's going to be two things that are coming towards you that are going to look like little hands coming towards you. And there's going to be two things that are going to be going away from you when you build your model, okay? So you're going to have a little bit more of a challenging time building this model over here. The other thing that's going to be challenging is there's no hydrogen here. So you will have to assign somebody to be the lowest ranked substituent. So let's look at the substituents that are attached here. We have a bromine, a chlorine, a methyl group, and an ethyl group. Of those four things that I just named, who has the highest molecular weight? Bromine, chlorine, or carbon?
Bromine.
Bromine.
Bromine has the highest molecular weight, so this is going to be your blue substituent. Can you see that? What color is going to be chlorine?
Red.
Red.
Chlorine is going to be red. And then we have to decide between the methyl group and the ethyl, who gets the highest ranking. What do you think? CH3 or CH2 that is attached to another carbon? Who has the higher ranking?
The ethyl.
The ethyl group has the higher ranking because not only do you have carbon, it is attached to another carbon, okay? So this is your yellow substituent, and the methyl group is gonna be your lowest rank, and you can just use the white ball to describe this methyl substituent for now, okay? So you're making a model in which the blue and the yellow are coming towards you. They're trying to give you a hug. The blue is on your left-hand side, the yellow is on your right-hand side. And then towards the back, you have the chlorine going away from you on the top. And I'm sorry, that's not true. The chlorine is going away from you on the top and the yellow is going away from you on the bottom. And in front of you, you have blue and white. So does your model look something like that right now? Do you have blue and white coming towards you? And do you have yellow and red going away from you? Do you have that? Yeah? Okay. If that's the case, now you can turn your model and you can figure out whether you're, when you go from blue to red to yellow, whether you're going to the right or you're going to the left. Which one are you going to?
To the left.
To the left. So that means this one here is the S enantiomer of that compound. Got it?
Right.
Okay. Now, has anybody already done this one and can tell us whether this one is R or S? You can take the time to do it. This one is easier to do because it looks more like a normal model.
It's R.
And you can take all the time that you need, but after you get it done, you will see that this one is the R enantiomer, okay? So one is R and one is S, and they are enantiomers of each other. So let me stop sharing this for a second so I can switch questions. Is everybody more or less catching up on how to do the models and how to do R and S? Slowly but surely, is it happening? Okay,
Yeah.
thanks for the thumbs up, Madeline. I can see you now.
I'm still a little confused on the first one. On the right side, how that one is, I keep getting R for that, not S.
Okay, Kara, let me put it back up and let me share the screen again so you can tell me what you mean.
That's the same for me. I get R for the second one.
I get R for both of them.
Yeah.
For this one? For
Yeah.
this one here? You get
Mhm.
R?
Yeah.
Okay.
No, the
Here,
one below.
this one?
I think we're on 2 separate pages.
Oh, I'm sorry.
Okay, let's go back here. Everybody can see the same thing that I can see? This pair of structures up here? Okay. Is this the one, Carrie, that you're saying that you're getting R?
Yeah.
Okay. So did you build your model?
I don't actually have a model. It's at school.
Okay, so what I need you to do, Carrie, I think the reason why you're not getting it right is because you're not using the model set. Is there any chance that you could build a quick one out of marshmallows once we're done with this and we can talk about it?
Yeah, that was actually a good idea. I'll probably do that.
Carrie, there's different things that you can use that you may have around the house that might work. You could use marshmallows. You could use corks. If you have any wine corks, you could use that. I have a student that made a very good one with 2 Q-tips kind of bent around each other. And then you color them with a Sharpie marker. So take your time to get your model done, and you and I can talk later once you have something going on, and we can see whether you have R or S, okay?
All right, thank you.
Okay, and anybody else who wants to talk about it, we can wait until you have made a model set, and then we can meet later on Zoom. That's not a problem at all. Got it? Okay, so before we run out of time, I want to look at the question that has been given Tim all kinds of gray hairs, which is the question about nadolol, which I think was the last one on the homework set. So let me get to that one. That's not the one. Just give me a second until I find it. Okay, so here is the structure of nadolol, and we are going to talk about how many enantiomer how many chiral carbons are in nadolol. Okay, here we go. And hopefully, can everybody see the structure on screen now? On my little cursor moving? Yep. Okay. So in this case, they have given us a slightly easier challenge here because there's lots of carbons that are not going to be chiral, and we can write those off right away. For example, can this carbon ever be chiral?
No.
It's a CH3, so no, right? How about this one? No. How about this one? No. How about this carbon right here in the middle? Can that carbon be chiral? There's 3 methyl groups attached to it. Can it be chiral?
No.
Then we have a nitrogen here. Nitrogen cannot be chiral. Only carbons can be chiral. Okay, so this nitrogen is a no-go. We don't even have to look at it. How about this carbon down here? What's going on with it? There's only 2 substituents that are shown. What are the other 2 substituents?
Hydrogens.
There would be hydrogens, so nobody would really care about them, right? So is this carbon ever going to be chiral?
No.
How about the carbon right here, the one that I'm pointing to right now? There's one thing that's not shown, which is a hydrogen, right? So this carbon has a hydrogen, it has an OH, and it has a CH2 on this side and a CH2 on the other side. Should we keep looking after this CH2?
Yes.
Yes. If we keep looking in this direction, we find the nitrogen. If we keep looking in this direction, we find an oxygen. Are those two different things? Yes. So this carbon right here is definitely going to be a chiral carbon. Can everybody see that? Okay. Now, the next carbon on the list here is a CH2. Can CH2s be chiral?
No.
So this carbon cannot be chiral. Then we get to all these carbons here in the benzene ring. And you know that every single carbon in a benzene ring is double bonded to carbon, at least on one side, right? So can this carbon here be chiral?
No.
No, because it's in a double bond, right? So that carbon cannot be chiral. How about the one down here? Can this carbon be chiral?
No.
No, because of the double bond. This one?
Oh.
No, because of the double bond. And the same is true for all the carbons that make the benzene ring. They cannot be chiral because they're attached to a double bond, right? That leaves us with 1, 2, 3, and 4 candidates up here that we have to consider. So let's start by considering this one here. This is a CH2. Can CH2s be chiral?
No.
No. Can this CH2 be chiral?
No.
No. So now we need to consider these two guys. Let's start with the one on the top, okay? There's something that's not being shown on that carbon because we're in a line structure. What is it that is not being shown?
Hydrogen.
A hydrogen. So there's hydrogen and there's OH. On this side, there's a CH2. On this side, there's a carbon that is bonded to oxygen. Is that carbon that I'm pointing to right now, Kyle? Is it stereocenter?
Yes.
Okay, that is a chiral center. And then the last candidate is right here. Again, line structure. So there's a hydrogen that is not being shown, right? We have a hydrogen. We have a hydroxyl group, the alcohol here. We have a carbon that goes to another OH, and we have a CH2. Is that 4 different things?
Yes.
It is. So is this carbon chiral?
Yes.
Yes, it is. So we have 1 here, 2 here, and 3 here, and those are the chiral centers in the structure of nalolol. So this person, who I don't know who it is, has the answer wrong. He or she thought there were 4 chiral centers. There's only 3. Again, 1, 2, and 3. Okay.
I have a question about that.
Yeah.
So for the one, like both of those two OH groups, why would it be chiral if like itself is an OH and then it goes to a carbon with another OH?
That's a good question. See, are you looking at this carbon here?
Mm-hmm.
Do you see how this OH is directly attached to this carbon?
Yeah.
If I was going to list the substituents attached to this carbon, if I was going to make a list and write down their names, okay? What would be the name of this substituent? Let's just pretend that we're going to call it OH, okay? So this is an OH directly attached to this carbon. When you look this way, before you get to the next OH, you go past this carbon, right? So if you were going to name this guy would be called CHOH, right? Because it's further away. So this substituent here is different from having an OH directly attached to it, right?
Okay.
You see where the difference is? And then this guy, we would call it CH2, and the hydrogen that is attached there, we would just call it hydrogen. One thing that might be very helpful, Zia, is to highlight the carbon that you're considering, or put a circle around it, or a star on it, or something, just so you know which one is the one that you're considering, and figure out if the substituents are identical or not. An OH directly attached to this carbon is not the same as a neighboring carbon that has an OH attached to it. See where the difference is?
Yeah. Mm-hmm.
Yeah. So that those are all things that we need to visualize so we can be successful with this kind of problem. Okay? I'm going to stop sharing the screen just to see the chat and see if anybody has. Okay. Yes, Tim, you did get it wrong because you put it as 3 and not the number 3, but I can give you another submission if you need it. So that's not a problem. And that's not just for Tim. Anybody who needs extra submissions or extra attempts, you just let me know. Okay? So do you guys feel like we're moving in the right direction with this? Are you starting to understand what's going on here?
Yes.
Yeah. Nicole, did you have a question?
Nope, no questions.
We good? Anybody else has any questions?
Can we go back to number 2 on homework real quick? On 2, the second one, is that one also S?
On 2, the second one. Hold on one second, Caitlin. Let me find it.
Thank you.
I'll put it on the screen for you. Question 2. Data structures. Here we go. I can share that now. Sorry, my internet is a little bit sluggish, but we will get there. All right. So what's your question about these two guys?
Yes.
So one of those guys is R and one of those guys is S. And which one is which one? I will tell you. The first one there, the first one that you made, was this one R or S?
S, I think.
The first one had, I'm checking my model set to answer your question.
I could have built it
This one
wrong.
has the bromine pointing towards you, right? The first one here had the bromine pointing towards you, and the lowest rank substituent, which be white, was also pointing towards you. And then he had the chlorine on the top, and he had the yellow substituent on the bottom. So when I make a model of the first one, the bromine and the lowest rank substituent are facing towards me. Good gracious, there we go. This is what my model of the first one looks like. And the chlorine and the yellow are going away from me. Is that what your model looks like, Caitlin?
Yes.
And then if I hold it by the hydrogen and I put the hydrogen towards the back, trace a path there from blue to red to yellow. Which direction are you going?
Left. So it's
Left. So that's definitely the S enantiomer. So this guy here is S, okay? Now let's build a model of this one right here. The bromine should be pointing towards the top. The chlorine should be pointing towards the side in front of me. The yellow substituent should be pointing towards me. And the white substituent should be pointing away from me. So if I hold it so that it looks like the picture on the screen, it would look like this. And if I hold that back so that you can go from blue to red to yellow, which direction are you going if you're doing mine?
right.
To the right.
Yeah, I think I built it
Are
wrong earlier.
enantiomers of each other. Caitlin, another easy way to check that they're enantiomers of each other is see if you can use the same model set without breaking it up to do both of them.
Okay.
If you can, they can't be enantiomers. You have to break the model and rebuild it in a different place to make the other enantiomer. Does
Okay.
that make sense?
Yes, it does.
Professor Williams, just to clarify about that one, for 2B, the first one is S and the second one is R, correct?
Yes. Mm-hmm.
Okay. I'm struggling from the picture of 2, just figuring out how the atoms are organized, or the elements are not atoms.
Okay, Christine, for that one, you need to recognize if there is a wedge, those atoms are coming out of the paper and towards you, okay?
Okay.
The ones that are on dashes are pointing away from you and therefore are going away from you in the plane of the paper. Does that make sense?
Okay. Yes, ma'am.
Yeah, if you hold it that way, it will make more sense.
Okay.
A question here on the chat. Let me see if I understand it. For 4, just to be clear, we look at the carbon that has the H display clearly. and consider all other connected substituents for R and S. Tim, I'm not sure that I understand your question. Do you think you could rephrase that or clarify? Or anybody else who's looking at the chat, can you help me understand Tim's question? I want to make sure that we get to it.
I also have a question about number 4. So, I mean, if you want to go over it.
Let's
That would be
open number
great.
4 then. Okay, number 4 is the enantiomers of naproxen. Oh, I see your question now, Tim. That was silly of me. I see what you meant. Hold on. Let me share that screen. Okay, how are you going to find the enantiomers in naproxen, right? Well, we just learned that there's a whole bunch of people here who cannot be chiral carbons, right? Can this guy be a chiral carbon?
No.
No. Can any of the carbons that are in the benzene rings, can they be chiral carbons?
No.
No. Can this guy over here that has a double bond to oxygen be a chiral carbon?
No.
No. So literally the only candidate that we have is this one here, the one that I have my cursor on, okay? So you have a hydrogen, you have a methyl group, you have this big group that has a double bond to oxygen here, and you have this carbon that is double bonded to carbon over here, okay? So you just need to build a model of what you see right in front of you right now. So in this model, who would be the blue substituent? Well, let me start by asking the question in a simpler way. Would methyl be the yellow substituent? Would it be the lowest ranked?
No.
Just a second.
Yes. Hydrogen is the super low rank, right? So it's the white.
Yeah.
Methyl would be the yellow substituent. Now you guys have to decide between this carbon here and this carbon in the benzene ring, who's going to have the higher priority? This carbon is double bonded to oxygen. This carbon is double bonded to carbon. Which one of those is double bonded to the thing with the higher molecular weight?
The one to oxygen.
The one that's double bonded to oxygen, right? So what is that going to be? Your blue or your red substituent?
Or blue.
Red. Blue.
That again, I'm sorry, I couldn't hear you.
Blue.
Blue.
Blue substituent. So if you build a model of what you can see there, right? And you turn that model, which direction would you be going? Let me put this on screen. Which direction would you be going here? Blue, red, yellow. Are we going to the right or are we going to the left?
Left.
We're going to the left. If you guys don't see my screen correctly, you may be mirroring your screen. So build your own model, okay? This is blue, this is red, this is yellow. If you build a model of that and you turn the model so that the hydrogen faces away from you, you will get the S enantiomer as a result.
Why would the CH be higher than the CH3?
This guy be higher than this guy?
No, the one attached to the benzene.
The one attached to the benzene is a carbon that is bonded to 2 other carbons, and one of those is a double bond. That counts to 1, 2, and 3 bonds to carbon. That is much higher than being bonded to hydrogen 3 times.
Oh, okay.
This guy is bonded to hydrogen 3 times. This guy is technically bonded to carbon 3 times. So that counts as being higher, okay? The reason why this guy counts as being even higher is because it's double bonded to oxygen and oxygen has a higher molecular weight, right? So blue substituent, red substituent, yellow substituent. Build your model and make sure that that model makes sense and that the model does what you're asking it to do. Turn it towards you and make sure that you're going to the left. It's very easy to get this question right because there's only 2 enantiomers, right? R and S, and you have 3 submissions. So everybody can get this question right on the homework. The reason why this question is important is so you can get it right when you get to the test. So if this question is not working for you, we need to make it work for you. Does that make sense?
Yes, ma'am. Do you mind just one more time? I don't know why I'm struggling so much with how to build these, but do you mind walking us through who's on top, who's like going to the back, and like who's in what
Okay, so
organization?
this is what I'm going to try to do, Christine. I'm going to point to everything here. Can you see my picture on the little screen?
I can't. I'm
It's
not
really hard to see,
sure.
right?
I'm still trying to figure out how to like do. Okay, here we go.
How to-
That's better.
How to orient things.
Yes, ma'am.
Okay, so let's talk about this here flat on the paper first, and make sure that you have your model set close by, okay? Do you see that this hydrogen here is on a wedge and therefore is supposed to be coming out of the paper and towards you? You see that?
Yes.
And do you see this methyl group, which is yellow, and it's supposed to be going away from you?
Yes.
Okay. Do you have your model set in front of you with the hydrogen pointing towards you and the yellow piece going away from you?
Yes.
Okay. Now that you have that, are there two empty places on the bottom of your model set where we could put these two things? Did you have?
You said the bottom of my model set, like, I don't know. Here, let
me see. Let me
see.
Move things so that it makes sense.
Okay, I'm starting video. So I have, here's my hydrogen, and then here's my CH30.
Yellow. Okay. Can we make sure that that hydrogen is pointing towards you, directly towards Christine? Uh-huh.
Okay.
Okay. Now, in the picture, the hydrogen and the methyl group are both on the top of the structure. So before you put anything else on it, could you flip that so they point to the top? Perfect. Now, do you see two empty spots? Keep it pointing towards you. I can see you perfectly. Do you see two empty spots on the bottom of your model set?
Yes, ma'am.
Okay, I need you to put the blue pointing in the direction of your right hand, and I need you to put the red pointing in the direction of your left hand. You got them?
Yes, ma'am. I'm going to take a picture of this.
We're recording this, Christine. You can see yourself on video later if you need to. Okay, now hold it by the hydrogen and make the hydrogen point away from you. And you should see three substituents that are right in front of you, right?
Yes, ma'am.
See them. Now go from blue to red to yellow. Which direction are you going?
To the left, so it'd be an S in Animer.
Okay, I need to see a much bigger hand gesture from you going to the left. I need you to be like waiting at the stadium. Are you going to the left?
Yes, ma'am.
Yes, you are, because that is the S in Antimer. Does that make sense?
Yes, ma'am.
Okay, so that wasn't helpful just to you. That was helpful to anybody else who might be watching. So thank you for that.
Yeah, well, thank you. I appreciate it. I feel like I'm struggling with the spatial construction of a lot of these.
And that's why we're going to practice this until we get it. And we're going to use our model set when we're taking the test. And we're going to do big hand gestures so we don't get it wrong.
Okay, thank you. I appreciate it.
Okay, is there anybody else that still has any questions left, or can we close now? Are we more
Good.
or less good?
Yep.
Okay.
Thank you.
Well, I hope you guys are doing very well with everything else. I will post everything that we need for the next section, which is going to be chapter 7 this afternoon. And I will see you next Tuesday so we can have another review. Okay? I'm going to stop recording now.
Thank you.
Or I'm going to try to stop recording.